Okay, let's have a look at this question now. Use de Morgan's theorem to show that Z1 and Z2 are two roots of the equation Z5 minus 1 equals to 0. Okay, so Z power 5 is equal to 1. Z power 5 is equal to cos 2n pi. This is in general polar form, the number 1. That's kind of a common one you should know in general polar form. So using de Morgan's theorem, you just divide by 5, so you get 2n pi over 5 plus I sine 2n pi over 5. And then you just have to set n to equal 4, 2. We'll make the 4 there, or 4. And that ends the proof. We showed that these are both roots, because that's when n is 2 and that one is when n is 4. And then show that Z1 times Z2 is a root of the equation. Okay, so Z1 times Z2. Now I think by Z1, I think that's maybe what I would call Z0 when I said n is 0. So that would be cos 0 plus I sine 0 times cos 2 pi over 5 plus I sine 2 pi over 5. When you multiply polar forms, the angles add. So that will equal, oh yeah, and also because that's 1 actually, yeah. So that's back equal to Z2. I'm assuming Z1 corresponds with n equals 0. I mean to say n equal, oh no it doesn't because it lists it there. That's Z1 and Z2, all right. I forgot about that. Z1 and Z2 are given. Right, so you just have to add the angles. So it just becomes cos 12 pi over 5 plus I sine 12 pi over 5. Now, because cos repeats after 2 pi, this is the same as cos 2 pi over 5 plus I sine 2 pi over 5 because it repeats itself every 2 pi, which is when n is 1. So, yeah. Okay. Are they roots? Well, that would be set to the power of minus 1, which would be cos minus 4 pi over 5 plus I sine minus 4 pi over 5. Which is cos 6 pi over 5 plus I sine 6 pi over 5. Again, because the the 2 pi nature here. These, you can check them on the calculator. These are the same. If you check, you get the same. Minus 4 pi over 5 is the same as 6 pi over 5 when calculating cos and sine. And that looks like when n is 3. So I'm just out of space, but if I just squeeze it in here maybe, so what happens when you get z2 to the minus 1? Just repeating the same thing I did there. That will end up being, I'll just write etc. here. It's the same technique here. Cos 2 pi over 5 plus I sine 2 pi over 5. So that's when n is, oh yeah, we had that earlier. When n is 1. So yeah, it looks like it's a yes for that as well. Okay, great. It's kind of a long first part. Okay. Now the B part here. On the Argand diagram, plot that set. All right. Let's just make, like, for example, when x is 0, y will be equal to 2 over 3. And then likewise, when y is 0, x will equal minus 2 over 3. So just very here and here. So there you go. That's k. W equals 3z plus 2. That's u plus iv equals 3x plus y plus 2. So u plus iv equals 3x plus 3y. Oh, the 2 is with the x. 3x plus 2 plus 3y. 3x plus 2, yeah. Express u and v in terms of x and y. So u equals 3x plus 2 and y equals, v equals 3y. So then if you look at k and the image of k, so our first one we'll have is 0 plus 2/3 I. So the u becomes 3 times 0 plus 2 is 2, and the y is just tripled, so that's 2i. And then if we take our other point, minus 2/3 plus 0i, the u becomes 3 times that, so that's minus 2 plus 2 is 0. And then the v is just 3 times y. Oh, that's 0 as well. So that becomes 2, 2, which is like up here, and 0, 0. Does that end up being parallel? Yeah, because that's 2/3 and that's 2/3, so that's K and that's its image. So if it made it 3 times bigger and then translate it to the right 2 units. So if that becomes 3 times bigger, 2/3 would become 2, and then you add 2 units to it. Yeah, so it would, yeah, so that would get mapped over to there. And then this one here, minus 2/3 times 3 is minus 2, so that would get there, and then get, yeah, so yeah. So that gets pushed up to there, and that gets pushed out to there. Yeah, okay.